Hey everybody, this is Mr. Beckstrom and welcome to section 6.1. This is on velocity and net change. And this is very similar to one of the other ones we did where we talked about velocity, position, and displacement. Instead, now that we have the idea or the definition of the antiderivative, instead of just going from position to velocity to acceleration, we can actually go back the other way too, using the idea of these integrals with antiderivatives. So let's kind of go over it and then we'll look at an example. So the first one says the position of an object at time t denoted by s of t, so s is the position function, is the location of the object relative to the origin. So when we use the s here, that means we're looking at the position as some point travels along the straight line, and we're going to talk about both the total distance traveled and the displacement of that point. The velocity of an object is basically just the derivative of the objective function, and we've already done that before. The displacement of the object, and let's talk a little bit about the difference between the displacement and the distance traveled. So if I have a straight line here, I'll make this as straight as possible. Oh, not too bad, right? And let's say I have a point that starts here. Some point starts right here. And let's say it travels over to right here, and then it travels back to over right there. And it ends right here. So the displacement of this point is just going to be this distance right here. It's just the distance between where it started and where it ended. So that distance there is going to be the displacement. And we can find that by basically just using that fundamental theorem of calculus part 2 and taking the antiderivative of the velocity function and evaluating it at the upper limit and then minus the evaluation at the lower limit there. And that's going to give us that displacement, right? It's not going to tell us anything that it went over here and then it went all the way back there. It could have done an infinite number of different travels before it ended up at this point, but the displacement is only going to tell us where it is compared to the initial starting point. Now the distance traveled, that's going to give us a lot more information, and we denote that by the absolute value of our velocity function or speed, and that is going to show the entire distance. So it's going to take this distance here and it's going to add it to this distance over here, and it's going to give us the total distance that this point traveled to get here. So as we can see that the displacement is really always going to be less than or equal to the total distance traveled. And we can find that by, let's take a look at, oops, I can do a little bit better than that. There we go. So let's say we have a curve and it goes like this, right? And here is B over there. A is right at the origin, and we're trying to find the displacement. Well, remember, and when we talked about this, using a definite integral from A to B, it's going to take this area here and then as a positive value, and then this area here as a negative value. So if these areas are actually the same, then we're just going to get 0, right? And that's not going to really give us a whole lot of information. It's just going to give us, it's just going to let us know that the area on top was equal to the area on the bottom. And if the area on the bottom was a little bit larger, which it looks like in this case it is, then we should end up with a negative value, right? Because we're subtracting out this area and we're adding in this area. Now, what does this absolute value do? Well, it takes any area that's on the bottom and it kind of reflects it to the top here. So it's going to take this area and reflect it up here. Therefore, we're going to have to know this point where it crosses the x-intercept, and we can do that by finding roots of the function and evaluating the integral separately. So we can add any parts above and then any parts below. We can just take the opposite sign of those in order to put them above, and that's going to give us the total area, which is similar to the total distance traveled here of our function. All right, let's go ahead and take a look at an exercise here. All right, so here we're going to go ahead and determine when the motion is in the positive direction and when it is in the negative direction. That means when it's, if you put this on a straight line, when it's traveling right, we'll call right the positive direction and left the negative direction. The second, we're going to find the displacement over the given interval. So like we said, that's going to be the difference between the starting point and the ending point. And then lastly, we're going to find the total distance traveled over that given interval. That's going to be how far it took to get there. All right, so let's go ahead and look over this. So the first one says determine when the motion is in positive and negative direction. So this is the velocity. And when the velocity is positive, that means it's going in the positive direction, which we're going to call right. And when the velocity is negative, it's going to go in the negative direction. So how do we find the difference between those positive and negative values for velocity? Well, it's just going to be where it crosses the x-axis. So we're going to find the roots. So we need to set this equal to 0 to find those roots, and then take a test point in each one of those intervals. All right, so let's go ahead and set this equal to 0. So that's going to be, and I'll factor a 3 out here. So that's going to be 3, and we're going to have t squared minus 6t plus 8. And that's going to be set equal to 0. And then we're going to find the roots, and if you just ignore the 3, set that equal to 0, you're going to pretty easily find that t is equal to 2 and 4. So these are the two places where this graph here for the velocity function will cross the x-intercept and x-axis, excuse me. So let's go ahead and set up our little interval here. So I'll put a little 2, I'll put a little 4, and then we can take test points somewhere here. So if we took 0 and we put that in the function, we're going to get a 24. That's pretty easy. So we'll get a positive. And then between 2 and 4, let's take 3 and evaluate it. I already put it into the calculator here. So let us go ahead and I put it into this function right here. So if we go to our, I put it in Y1 table here, delete these. And we put 0 in there. Notice we get that positive value for y. If we put a 3 in there, which is right between the 2 and the 4, we get a negative value for y. And if I put anything larger than a 4, let's just be silly and put 100 in there, we'll get a positive value for y. So it's going to be positive, negative, positive. That means it's heading in the positive direction between, so positive direction between negative infinity and 2, and also between 4 and positive infinity. And then it's heading in the negative direction between 2 and 4. All right, so this tells us right here that we're definitely over the interval from 0 to 5. Our displacement is definitely going to be less than our distance traveled because this thing changes directions a couple of times between 0 and 5. All right, the next one says find the displacement over the given interval. So displacement here is just using that fundamental theorem of calculus part 2, and it's going to tell us where it is at the ending point relative to the starting point. So let's go ahead and do that. So that's going to be just from 0 to 5, and of our function 3t squared minus 18t plus 24. All right, and this is going to be dt. So this is the definite integral that we want to find. Make that a 0 there. All right, so this, taking the antiderivative using the power rule, that's going to be 3t cubed over 3, which is just going to be t cubed. And then this is going to be minus 18t squared over 2, which is just minus 9t squared. And then plus 24t plus 24t t, and we're going to evaluate this from 0 to 5. So we're going to plug 5 in this function, and then we're going to minus, and then we're going to plug 0 in this function. And that's how we're going to do it. So once again, save a little bit of time here. I already put that in my calculator for y2. So to find that displacement here, one way I can do it is I can go vars, go to y variable, bring up my y2, and remember, so it's going to bring up this function here, and I want to evaluate it at 5. So I'll do that, and then I'm going to do minus, and then same thing, vars over variables, y2, and minus the function evaluated at 0. And I get a displacement of 20. That means that I am 20 to the right of wherever I started from on my line. So if my line is right here, and I end right here, so I start here, I end here, and this distance here is 20. 20, I don't know if it gives the, let's say it's meters, 20 meters. Okay, so this is A over here, this is B over there, so let's do C. Now C is going to be a little bit longer, but I think we can do it here. So C, they want us to find the area traveled. So remember what that is. That is from A to B, and it's taking the absolute value of our velocity function with respect to t. And the absolute value means that we need to only look at the portions that are above the x-axis. And notice that the portions that are above the x-axis are going to be between 0 and 2 and between 4 and 5, which means that the area below the x-axis is going to be, we're going to have to multiply that by a negative to make that area a positive area, because it's already going to be a negative area below. And before we do this, let's go ahead and take a look at the graph of it. So if I go to y equals, and let's go ahead and turn this one off. And so I only want to look at this one here, and on my window, I just want to go from 0 to 5. And let's see if it gets it all in there. Not quite. Looks like I have to go higher. So I'm going to go back up here to my window. And my y min is, I'll change that to -5. And my y max, let's go up to like 50. See if that does it. And change the scaling to 5. Just looks a little prettier. And there we go. So we're calculating this area here, and then we're going to take this negative area down here and put it above the, reflected above the x-axis, so we get a positive area there, and we can do that just by multiplying the function by a negative, and then we are going to add in this area here. So one way I can do this with my calculator, well, let's actually do it on paper first, and then we're going to use our calculator. So this is going to be equal to, so first we're going to go from 0 to 2 of our function here. So 3t squared minus 18t plus 24 dt. All right, so we're adding this area in. And then this area here is going to be a negative. So if I subtract a negative, that's going to give me the positive version. So I can subtract from 2 to 3 of the same function, 3t squared minus 18t plus 24. Oh, hold on just a moment. All right, dt. And then this last area here is going to be positive, so we're just going to add that. So that's going to be from, this one should be from 2 to 4. Did I put a 3 there? I'm sorry. Let me erase that. And let's go back and put a 4 there. Just wasn't paying attention. And then we're going to go from 4 to 5. And we can add that area because it's already going to be positive of 3t squared minus 18t plus 24 dt. Now this is a whole lot of math to do. So instead of doing all that math, let's go ahead, find these three areas separately in our calculator, and then we'll just add them together. So going up to calculator here. Out here. So the first one, so we're going to do this just from 0 to 2. 0 to 2. So we're going to do bars, variables. So this first one evaluated at 2. And then minus. Do the same thing here. Evaluated at 0. And that's going to give us the first, oh look at that, the displacement or the distance traveled from 0 to 2 is actually equal to the entire displacement, which means that this portion between 2 and 4 should be the same amount as the portion from 4 to 5. So these two parts should cancel out. So whatever we get for the next one, from between 2 and 4, should be the same area as 4 to 5, because they're going to end up having to cancel out to give us that total. Alright, so let's go to 2 to 4 first. So we'll do the same thing, vars. Remember, you start with the upper limit here. So y2 evaluated at 4 minus vars y2 evaluated at 2, and that's going to give us a negative 4, which means that our last one is probably going to give us a positive 4. Alright, so then we're going to do vars y2 evaluated at 5, and then minus vars function y2 evaluated at 4. And sure enough, those parts cancel out. So when we're looking at the total displacement, it's going to be 20 minus a negative 4, which is plus a 4, plus a 4. So that's going to be a total of 28. So our total our total distance traveled is 28, but our displacement is just 20. Alright guys, I hope this helps. Please let me know if you have any other questions, and have a great rest of your week. Thanks.